Okay, so last time we talked about density estimation. So the idea of density estimation can be traced back to our statistical functional and using the empirical CDF to plug in the true CDF to get an estimator. But something we have to know specifically is that, so here, we're not directly doing the plugin, because the thing is that we need to actually express our density function in terms of our CDF function, right? And then we plug in the CDF. So the idea here is to go back to the definition of the density function as a derivative. And we know the derivative can be defined as a limit, right? And the limit can be basically the difference of your CDF functions in a small neighborhood of y, and then you divide that difference. Basically, you have y plus h as the upper bound. You take the f CDF value at the upper bound minus the CDF value at the lower bound of the window, and you divide that by the window length, 2h. And the limit of that is the derivative of f at big F at y, and we write that small fy. So the reason we need to do this is because we have to use the plugin for the CDF function, and we're not we don't know how to define the empirical version of the density, right? We don't know what is f hat, and that is the question we want to address here. So the statistical function is all about using h at fn hat to plug in as an estimator of h of f, right? So that is the whole idea. All right. So, and the reason we need to go back to this is because f(n) hat itself doesn't have a derivative at many places, because it can be discontinuous, right? As empirical CDF. So that's why we have to use the definition of derivative. Instead of requiring f(n) hat to be differentiable, we go back to the definition of derivative as a limit. And this limit doesn't require, you see, it does not require any differentiability. It's just about the difference of f. Okay, so therefore, the plug-in version is naturally this one. We're changing f to fn hat, the empirical CDF, and everything stays. And we call that the density, or we call that the density estimator. But if we think about it, this is essentially corresponding to a kernel of this uniform form. That is, we give uniform density to data points in this interval from y minus h to y plus h. Outside of interval, we assign the weight to 0. So this is how we use data points to help us estimate this density of y. Essentially, we're using a sample x1 to xm, but only within the sample, the data points that are in this interval are used for estimating this y density. Okay, so this is like the preliminary form of our kernel density estimator, where the kernel is discontinuous. It has uniform density values in the interval, 0 density values outside of interval. And we think this may not be ideal intuitively because we have too much reliance on this h, right? Because within this h length interval or outside of the interval, you just have a sharp difference in terms of your sample usage. Then the question is whether we can have a more continuous way of using the sample. And that is where we get this form. So this is what we talk about, the kernel density estimator, and the k is a kernel function. So the previous one we actually have is k is just a uniform density. Within this interval, it has uniform density, outside of interval, 0 density. But other possibilities of the kernel estimator can include Gaussian, right? Gaussian is continuous. It will gradually decrease the weight of data points xj as xj gets away from y, but it's not like 1 or 0. It's not binary, included or excluded. So for all kernel density estimator, we need to specify this h, and that is called bandwidth. So essentially, intuitively, what the bandwidth does is you increase the H, then you will use more data points surrounding your Y to help estimate the density of Y. If you decrease the bandwidth, then you will use fewer data points surrounding Y to estimate the Y. But what is the optimal bandwidth? What's the intuition here? Of course, you want the bandwidth to be small, so you are estimating the density at Y, not actually an average density of the average of density in the neighborhoods of Y, right? The larger the bandwidth, the farther you get away from Y. But the problem here is we're doing estimation. So if our sample size is finite and if H is too small, then you may have too few data points in that window or next to Y, near Y. So then with such a small sample size, your estimation of the density of Y cannot be accurate. So it's always a trade-off between the available sample and also the accuracy. And this actually reflects what we call bias variance trade-off. Why is that? So bias means that the target you're estimating should better be the exact density at Y. So therefore, you don't want this neighborhood to be too big, right? Otherwise, you will introduce in bias. But the variance is actually due to sampling uncertainty or sampling variance. So that is, even though your target is accurate, you don't have a bias for your estimation. But if you have too few sample to support your estimation, then the variance can be too big. So it's a trade-off between the two things. Yeah, and then this idea, bias variance trade-off, is like I would say the most crucial key idea of statistic estimation. So for that purpose, you see, we actually need two conditions on H. This is what we said last time to make sure this density estimation can work. The first one is that your H should go down to 0 as your sample size goes to infinity. And this makes sense because if you have a large enough sample, then you can afford to have a small bandwidth because within that small bandwidth, you still have enough data points to support your estimation. Okay. The second thing is coming from the variance. Actually, if you want the variance to go down to 0, you actually need n times hn. Hn is the bandwidth that changes with n. You need their product to go to infinity. And this is to ensure you have asymptotics in your local neighborhood. That means my bandwidth decrease is slower than my sample size increase. So therefore, within my bandwidth, within my window, my sample size within that window is actually increasing. Okay, this is to guarantee the asymptotics. Okay, so just keep in mind the two conditions, n times hn going to infinity, hn going down to 0. And then we use calculation to derive what is the bias, what is the variance of a kernel density estimator. And this is what we have last time. And this is called a theorem. Essentially, it's about the bias and variance of Fn hat, the density estimator at Y. So please note that here we fix Y. So we're looking at a particular value Y and just estimate the density at that point. We're not talking about the overall density curve yet. Okay. So for this particular Y, the bias has like a dominant term that depends on the bandwidth square and the second derivative of Y. So what does second derivative reflect?
Concavity?
Yeah, it's about the curvature, right? So basically, you know, the first derivative reflects the slope, right? Local slope. And the second derivative reflects the curvature. And what this means is that if the second derivative, so let me just tell you this example for you to understand. Okay, so if this is my density function, then let me ask you, where does the density curve has the maximum in terms of absolute value of second derivative? Where does it have the maximum second derivative's absolute value? It should be here. It should be at the peak here because this is where the curvature changes is the curvature the biggest, right? And just comparison, if I have the density now change to this to be very flat, and then at the same peak value, the mode, here the second derivative will have a smaller absolute value. Okay. So, and what does this tell us? This tells us if the density is in the top case, estimating it from your sample is more difficult, right? Because essentially the sharper it is, then the smaller the, how do you say, the smaller the neighborhood you should go for, or the bandwidth, and then you have smaller sample size to support that. So it is a more challenging case to estimate this density than this density in general. So the bias actually depends on the neighborhood, right? You want the neighborhood to be small, bandwidth to be small. You don't have a significant bias. And also, if this curvature second derivative is too large, you also have a large bandwidth. And also, this tau term, tau square, depends on your kernel. So kernel kicks in, plays a role here. But anyway, this is the dominant term. And the remainder of their bias, HA, is HN squared. Since we know HN goes down to 0, then that term is smaller compared to this one in terms of the order, right? So that's why we'll put in small. That's the bias term. So it prefers to have a smaller bandwidth, in short. And the variance term is this one. So you see that here the dominant term is this integral. So basically we have 1 over n times hn here. And this is the density, true density value here. And this depends on your kernel choice. And the remainder is smaller compared to this one. Since we know n times hn goes to infinity, then 1 over this, its inverse goes down to 0. And this remainder goes down to 0 faster. So you will see that for this variance part, you actually prefer a larger bandwidth so you can have a larger sample size. And we know that the mean squared error of fn hat y for estimating fy is bias squared plus variance. We know that decomposition. This always holds. So let me grab this part. Yes. So this is the formula we have in general for estimator. Mean squared error is the expectation of their square difference can be decomposed as the variance square and variance plus variance. And this is just a general formula. And because of that, now I'm going to use this bias formula and variance formula to put them into this mean squared error. And my goal is to minimize this mean squared error. Okay, it's like an L2 loss. We want to minimize that. And you can see that by putting the bias square and variance in, this is what we get. So essentially, doing so, and you want to find the H value that minimize the two things. So essentially, you express this as an objective function to minimize in terms of H. Okay, so I just keep the key terms H fourth, and the other things I call them A. And then the second term is 1 over H. The other multiplier is called B. So I'm trying to minimize this, and it's just a calculus problem, right? I take the derivative against H, set that to 0. And this will turn out to give me this H. So B is what I have over here. A is what I have over here. So putting them in, and you can see that if we call this B, including this term 1 over n here, A has nothing to do with n. So basically, you see that only B relates to n. And if we want to study how H, the optimal H depends on n, sample size, we can put this back in. B is 1 over n in the order. So this will tell me H is in the order of 1 over n to the 1/5. So in other words, putting it here, and as we know that B, using our notation before, in the same order of 1 over n, okay, put this in, then H is in the same order of 1 over n to the 1/5. Or we can write n to the negative 1/5. That's it. So this is the optimal bandwidth, the order of the optimal bandwidth in terms of sample size. So what does this tell you? This tells you a rate, like how the bandwidth changes as your sample size increases. And now with this rate, right, now you know the order of n of in the order of n about h, you can put this back in here, and then you can get a rate for the mean squared error. So essentially, on the first term doesn't depend on, the first term now depends on m because of h, right? So you can see that this bias square is now in the order of n to the negative 4 to the 5. Okay, and for the second term, same thing. It's interesting. The rate is also n to the negative 4 to the 5. Yeah, so now we have this rate for the mean squared error. And there is a very important statement in studying the property, mathematical property or theoretical property of our estimator, is that how does the mean squared error go down to 0? In what rate? And now we get this rate. Okay, while for parametric models, remember, like when we estimate a population mean using the sample mean, right? These kind of estimators we talked before, central limit theorem type of estimators, we actually showed you that the order is for the CLT type of thing. So for example, we know that so for the CLT type of thing, we actually know that essentially we actually know this, but it's not related to the CLT result, but it's a separate fact that we know for this estimator, the rate is, let me just put it this way. Right, we know this go down to 0. And this go down to rate 0 at the rate of 1, oh, sorry, n to the negative 1. So 1 over m. So what does this mean is that for parametric cases, when estimating this parameter, right, the estimator is more efficient than the non-parametric case. So essentially, to achieve this rate, to achieve the same rate, we need a larger sample. Yeah, yeah. So in other words, it go down to 0 much slower than when we're estimating a parameter. So this is just a general fact. For non-parametric methods, the efficiency cannot be as good as parametric model. The reason is just because you are making less assumption about your distribution. If you don't assume anything, everything you learn is from your data, and then you need more sample size. Yeah, larger sample size to help you. Yeah. So you can see that in the classical sense, we don't have so much data available. We didn't have so much data available in the old days. So that's why a lot of the considerations was just how to use the sample more efficiently to get more things out of a small sample. And this is very different from the current time, right? For the applications where we have large data, big data. So in this case, I would say a lot of the issue is now become computation. How can you use the data? How can you analyze the data? And so that's why you see a lot of the shift in the field has been towards optimization, how to fit model efficiently and GPU, right? That changed a lot of the things. It's just because we now have more data than we can handle. But in the old days, we were actually in the scarcity of data. But I think nowadays, small data issue may still exist in many, many fields, especially science, like biomedical science, social science, where data collection remains to be challenging, even though you can have massive data on internet, right? So that's how we can build a large language model. Images, text on internet, but that's just part of the problem. And maybe for the subject you want to study, collecting data is still challenging. So I think the looking forward, I think it's we always need to think about how to combine those small data techniques with the big data techniques in a useful way. Okay, so that's the optimal bandwidth. Coming back, optimal bandwidth is on the order of n to the negative 1/5. So as a result, mean squared error is on the order of n to the negative 4/5. Okay, moving forward, we can talk about, so that is the mean squared error. Now we can talk about the integrated expected square error. This is the term used in this layman book, but also some people call this MISE. So MSE stands for mean squared error, and MISE stands for mean integrated squared error. So essentially, you're talking about integration over all possible values of y you want to evaluate density on. So therefore, your variance and bi-square both need to be integrated. But the integration doesn't actually change your dependence on the bandwidth or the n. So you still have h4 in the first term, 1 over hn in the second term. And if you still want to minimize the MISE in terms of h, you get the same order of h depending on m. It's just that the constant is now different. The constant is now integration instead of just f double prime at a particular y. That's it. Okay, so yeah, so that's it. So we have that order for the mean squared error and mean integrated squared error. Another question is whether you can use central limit theorem for a particular wise estimator, density estimator, and its expectation. Do we have something like a central limit theorem thing? Actually, yes. The reason is because the kernel density estimator is also something like an average. So as long as like an average type of statistic, the central limit theorem typically applies. But actually, for this one, you actually need a stronger condition to have the asymptotic normality. That is, you need to strengthen the second condition be from n times hn to infinity. You make this n times hn cubic. That goes to infinity. And so this means that your hn need to go down to 0 even more slowly than what you had for that consistency result, right? For that one, for mean squared error going down to 0 is just getting you consistency. You know that this fn hat at y will converge to expected fn hat at y in probability, right? You have that. But for this asymptotic normality, you actually need you need the bandwidth to go down more slowly. This is just to ensure that you have more sample. Yeah, more sample to support the central limit theorem thing. But just know that here, what we have put here is the expectation of f n hat y. It does not necessarily equal to f of y. So in other words, the central limit theorem is just saying that the estimator has asymptotic normal behavior around its mean, its expectation. But its mean, due to the existence of bias, may not be the true density. Yeah, so therefore the true density is another thing. Okay. Okay, so that's what I will say for density estimation. But finally, a question we can ask is this. Let me see. It's this one, MIS. So if you are interested in this, minimizing this mean integrated square error, you express it out in this form. So the remaining question we haven't talked about is how do you optimize kernel? Because you see, we talk about how to optimize the bandwidth, and the optimal bandwidth, if you just consider n, then the order is always n to the negative 1/5. But if you also want to consider the constant in your optimal bandwidth, then the constant will involve this tau and also this. So tau squared depends on k, kernel. This one depends on kernel, and this depends on just the second derivative of the true density. So the next question is, to minimize this mean integrated squared error, MISE, does there exist an optimal kernel that will make this smaller than any other choices of kernel? And yes, this is a valid question. And to answer this question, there were results in our literature. Okay, so tau can be expressed in terms of k. This is what we have, right? Tau involves k, and this involves k. So by minimizing this term, essentially we can show that the kernel should be this one. It's called a Panichanikov kernel. I think it's a Russian name and last name. So this kernel takes this parabola form, basically truncated in an interval. So you see that it's kind of like a smooth out or concentrated version of uniform kernel. Uniform just have a flat density in this interval from -1 to 1. And Gaussian just has a continuous decrease, right? As you get away from 0. But this one actually stops in the boundary of the uniform. It's only within -1 to 1, you have non-zero density. Outside of the interval, you have zero density. But inside the interval, it's not flat. You put more weight on data points, more density on data points surrounding your y, and take this parabola form. Yeah, so it was in the literature, and this is shown to be the optimal kernel. And of course, then the next question is, if I don't use this kernel, but I use some other kernels like Gaussian, like the uniform, and another possibility is, what if I do a triangle, right? I can just do a triangle within the interval. How much efficiency would I lose if I use these alternative kernels? And for this one, we actually talk about use this quantity or measure called asymptotic relative efficiency. And this is just to compare two estimators in terms of their asymptotic variances. Essentially, and we show this when we talk about using the sample mean or the sample median to estimate the population mean. Remember that. And we said that sample mean is more efficient, right? If the true distribution is Gaussian. Yeah, sample mean is more efficient. So anyway, so asymptotic relative efficiency is like the ratio of two estimators' asymptotic variances, but it's the reverse of the ratio. So essentially, if an estimator has a larger asymptotic variance, then it has a smaller asymptotic relative efficiency. Okay. Anyway, so looking at this, and this is what we get from calculation. Using normal, uniform, triangular, you lose somewhat efficiency, and you lose the most using uniform. Yeah, like the naive version, the plug-in version is the uniform, but you lose the most using that. And triangular gets closer to what we get from this optimal Epanichetkov, how to say it? Epanichetkov kernel. Yeah, we that is the optimal one. And normal is also in the middle. Okay. And this is something I already said before. No parametric density estimator can achieve the rate 1 over n. So that's just the reality. And our rate is this, n to the -4 over 5. Now let's look at some multivariate case. Okay, multivariate case means that now our sample are multidimensional and our distribution is also multidimensional. So this is known to be the curse of dimensionality. Whenever your dimension increases, it's more challenging in general. Yeah. And so here we just talk about this S-dimensional case. So suppose that we are interested in this density defined in an S-dimensional space. So at a particular value, now it becomes a vector y is S-dimensional. We can write it out as y1 to ys. Then correspondingly, our sample, NIID sample, will become NIID random vectors. So xj is the jth random vector in our sample. We can also write it out in the S-dimensional, right? S1, x1j to sxj from an S-dimensional distribution. And now the kernel density estimator can be generalized to this form. So we will need an S-dimensional kernel, not a one-dimensional kernel. And in every dimension, we evaluate the distance between a sample, right? Sample j, data point j, in every dimension to our target value in that dimension. Okay, and we can have a bandwidth in each dimension, h1 to hs. And we still need the symmetry of our kernel, but now it's in S-dimensional space. And also the kernel needs to have a symmetry, right? So it integrates to, and it has a, yeah, so its first moment is actually 0. So these are the generalizations. And one thing I want to say here is, so this S-dimensional kernel density estimator is still a valid density estimate, is still valid density itself as in the one-dimensional case. So there's no problem with that. And regarding the theory about the bias and variance type of things about our kernel density estimator, now since it's S-dimensional, we need to define partial derivatives of our true density. We need first order, second order, third order partial derivatives of F. Yeah, to have the theoretical results. So let me first jump to the conclusion. Okay, this is our bias. Okay, the bias is in this form, and the C's are just some relationship we specified between how to say, just about the bandwidth. This is still about the bandwidth. Remember, we previously have h to the fourth. Now we actually have c, I, c, j here, but they are also something we just defined to specify the bandwidth. So you can see this is the bias term, and this is the variance term. Okay, so the key thing here is that 1 over nh becomes 1 over nh to the power s compared to the one-dimensional case. This is the major change. So that's why you see that if we need this variance to go down to 0, our s needs to go down to 0 much slowly, more slowly than one-dimensional case. Because previously we just need n times h go to infinity. Now this will require n times h to the power s go to infinity. And then h has to go down to 0 even more slowly. Okay, and that means, okay, you, how to say, with such a larger bandwidth, then your bias will be a problem, because bias will be higher if bandwidth is large. Then how can you do, right? And this means that essentially you need to have a very, very large n to really do well. You have to have a very large n so that your bandwidth, even though it goes down to 0 more slowly than h, then it's still reasonably small, right? Yeah, so only a very large n can make this thing very large, even though h is small. And h needs to be small to make the bias good. So that just tied together. And then I can just directly jump to the conclusion for your intuition. This is the thing. So again, we do the same mean squared error equals bias square plus variance, and we want to minimize this. So this is what I said. You need h go down to 0, and you need n times h to the power s go to infinity. So then the optimal h should be of this order, which translates to n because b involves 1 over n. So this is the result. So instead of having h on the order of n to the minus 1 over 5, because that in that case s was 1, right? So that's why 1 plus 4 is 5. Now it becomes n to the negative 1 over s plus 4. So the larger the s, the slower h go down to 0 as n goes to infinity. Yeah, and then put this optimal h into our mean squared error. This is the rate of the mean squared error going down to 0. Again, it's more slowly, right? The larger the s, the slower the rate. So curse of dimensionality is here. So estimation becomes more and more difficult. Yeah. And so to summarize, let's look at the sample size required to actually make your estimation error, the mean squared error, actually not mean squared error, but this one, mean squared error divided by f squared y. So basically we'll normalize this depending on the density value here. So by this quantity, relative expected square error, this is the sample size we need. So if you just want this relative squared error to be less than 0.1, if you are just two-dimensional, not bad. You just need 19 points, sample size. Four-dimensional, hundreds. Six-dimensional, thousands. Eight-dimensional, yeah, so it's impossible, right? So you can see that it's getting worse and worse. So that's why dimension is always a crucial thing in our applications. Yeah. Okay, so that is kernel density estimation. Do we have any questions before we move on to our next topic? All right. If not, then we will conclude this functional part. So just to summarize, we introduced the statistical functional concept, and we said that a lot of the estimators we get can be considered as statistical functionals. And we talk about the V estimator, right? Basically a plugin. And then we said because of the plugin, direct plugin requires sample with replacement from your actual sample, right? You sample from F and hat is sample with replacement. And if your statistic depends on more than, or your parameter depends on more than two IID random variables or more than one IID random variables from your distribution, if that's how you define your functional, then expectation functional, then you may encounter bias in your V estimator. Then we introduce the U estimator on bias to remove the repeats. So we have the sample without replacement for the U estimator. That covers a large class of parameters which can be expressed as expectation functionals. Okay, then we talk about Bootstrap. We're saying that Bootstrap is essentially evaluating the performance of an estimator, and the performance metric or performance measure itself is a functional of your distribution. And we can replace that functional F by F and hat. Then we get the Bootstrap estimator of the performance metric. And then we said that direct plugin version can be require all enumerations of your sample, and that cannot be possible if your sample size N is large. So therefore, we use Monte Carlo instead of the actual enumeration of all possibilities under F and hat to get an approximate version for that. But essentially, Bootstrap is a plugin for the functional. Okay, that's all we said. So now we will move on to a new topic, and this topic is called efficient estimators and tests. So we want to actually, in this is the last chapter of the Layman book, and this is also something we didn't cover in previous years of this class. So it's new material like density estimation. And the reason I want to introduce this is because it's about the maximum likelihood estimator, which is probably the most widely used estimator in applications, right? If you can specify a reasonable distribution model for your data, then estimation can become maximum likelihood. You have basically an automatic way of doing that. Okay, so this chapter is about that. And it's interesting that there are some careful thinking needed so we can actually use this result confidently. Okay, so let's look at this. So why MLE is so widely used? It's because there is theory that establishes it is asymptotically efficient, meaning that it can achieve the minimum asymptotic variance to justify that it's good. Okay, so let's look at this paragraph first. The most widely used approach for such a construction, which in construct means constructing procedures that in some sense efficient, that is asymptotic optimal, is based on Fisher's maximum likelihood estimator and some of its modifications. So, with this MLE, it will actually make the statistical estimation problem more like automatic. You just worry about likelihood function and then how to optimize it, maximize it, instead of saying, okay, for each case, let me construct an estimator in a smart way. Right? That become case by case. To avoid certain difficulties, and this is the original source of this chapter, and replace the MLE by a consistent root, theta, and hat of likelihood equation. So this is something we'll show later. But the most important result is that when such MLE exists as the unique maximizer of the likelihood, we can show that under some conditions, it is asymptotically normal, and it has this variance 1 over Fisher information, which is also a very important quantity introduced by Fisher. Okay, we'll introduce those. And yeah, that's pretty much it. This is just the overall of this chapter. And finally, testing procedures, likelihood ratio test, wall test, route test will be introduced. Okay, so let's first look at maximum likelihood. So we'll just do a very quick review of the maximum likelihood and the likelihood so we can keep people on the same page. So I know likelihood is very, very commonly used, but it's interesting that in a lot of the applications of using likelihood, I can see many, how to say, misuse of the terminology. What do you mean by likelihood? So first of all, let's go back to the definition here. A starting point for the generation of such estimate is the method of maximum likelihood. Suppose for a moment that x is a discrete random quantity taking on values x with probabilities. Right? This is what we call the probability mass function, PMF. Depending on a parameter taking on values in omega. Omega is the parameter space. So for fixed x viewed as a function of theta, this probability is called the likelihood of theta and is denoted this way. So one thing we need to be sure is that likelihood is a function of parameter values. It is a parameter values function, while this probability mass function is a function of your random variables value. That is different. So even though we are defining the likelihood through this probability mass function, they are not the same thing in nature mathematically, because likelihood takes parameter value as input, while probability mass function takes random variable value as input. That's just different. Okay. And so in this case, you find the value of theta, you call that theta hat, such that this likelihood function is maximized. So in other words, you are depend on your observed value, small x, to find the maximum likelihood value, parameter value. And so that's why this theta hat depends on x. Because once you change this x, theta hat will change accordingly. Yeah, this is very important to know. So this assigns the largest possible probability to theta, which maximizes the likelihood. Yeah. Okay, so in a way, I think this is wrong. Down to the probability to x, it should be like this. Yeah, so to make the x value most probable. Yeah. Okay, and if we change x to be continuous, then we use its density, probability density function, PDF, and the likelihood is defined accordingly, and then you find the value that maximizes this. So in general, MLE is defined by maximizing the likelihood. So we can look at one simple case Poisson distribution. I think everyone here should be familiar with this. This is what we introduced in the undergrad class, right? So if you have y1 to yn IID from Poisson lambda, this is the likelihood function because of IID, right? Basically, the probability mass function of y1 to yn is just the product of each one's probability mass function. And by maximizing this, you can easily see that lambda hat is just the sample mean, sample average. However, there could be a non-existence of MLE. Why would that happen? And this is something you may not have seen before in an undergraduate context. So this is the case where your sample is not perfect, but it's just missing information. So the thing, or incomplete information. So for each I, we only observe yi being 0 or not, instead of the actual positive values of y. So from here, you actually get y1 to yn from Poisson. And Poisson can give you any, or depending on lambda, but you can get different non-negative integer values, right? But here we're just saying if yi is positive, we just observe 1. We don't know the actual value of yi. This is not complete information. But you can still use this xi to get likelihood of lambda. So because you know that for xi being 0, this is the probability. For xi being 1, this is the probability. So based on these two probabilities, I can still write the likelihood. Okay, I can still write this likelihood. So, and then I can try to maximize this likelihood. And this is the maximizer. But you can see the problem here is, and remember at each xi is just 0 or 1. Okay, so, but you will have a problem of what? if it's X bar, right, this X bar is just the average of Xi. If all of your Xi's are 1, if everything you observe is 1, like no zeros, X bar is 1. 1 minus 1 means what? 0. Log 0 is what? Negative infinity. And you put a negative sign here, you get positive infinity. So you could have a positive infinite MLE. And why is that? The reason is because if you only observe once, right, and it's from Poisson, and there's no way for you to know where exactly lambda is, because all these xi's being ones, they could correspond to yi's that are positive but small, or yi's that are positive but large, right? There's no way for you to know exactly. Yeah, and so this is the case where the MLE is undefined. But on the other case, if you did observe your sample that are all ones, the likelihood just becomes this form. And this form means what? This form means that if your lambda increases, the likelihood increases. So that's why you would tend to choose a large lambda. But on the other hand, if you fix your lambda, but you increase your n, you can see what? Then this probability that your sample is all ones will go down to 0. So this chance will be smaller and smaller as your n increases. So in other words, if you do have a large sample size, then the chance that you have this infinite MLE will be very unlikely. The chance will go down to 0. So basically X bar, the probability that X bar is exactly equal to 1 will go down to 0 as n go to infinity. That's just it. And then because of that, we can still study the asymptotic behavior of MLE. So in other words, as long as you have one xi that's 0, your MLE is properly defined. And asymptotically, that will happen with probability 1. So this is just to say that in the asymptotic case, it's actually easier because we can actually use that to argue that the extreme case for MLE being undefined won't happen. Okay, but at least this shows you one case where you might encounter some problems with MLE with your finite sample. Okay. And another example, which I think is quite how to say, contrived but interesting, it's actually from the book our previous lectures were based on Tom Ferguson, who was a retired professor from our department. Yeah, he was a professor here for many years before this department even existed. It was in the math department, and he was a professor there. And then with this new department established, he moved to this new department, and then he retired a couple of years ago. So the book he called The Large Sample Theory was the one we used for previous lectures. So he had this counterexample constructed. So without too much complication in reading the notations, let's just look at a figure. So he constructed this mixture. Okay, he constructed this mixture example. So in other words, and he constructed uniform density between 0 and 1, and this triangle density in this interval of theta minus c theta, theta plus c theta in this interval with this triangle as the density. And he would need the two sides to be within this interval. So in other words, as theta moves towards 1, the interval length should shrink. And then the density maximum will go up. That's the construction. So you see that if you move this triangle to this side, it will become narrower and narrower. If you move theta towards 1, the triangle will become narrower, and the spike will go up. And if you move to this side, then I think when the theta is at 1/2, then the triangle is the widest. Yeah. So essentially, he constructed this counterexample, and your sample is sample from this mixture distribution. But the problem here with the MLE, it can be shown mathematically, is that the MLE will always be at 1. The theta will be at 1. Theta will be at 1, regardless of where the true theta is. The reason is what? The reason is if you specify the theta to be at 1, then this triangle density will go to infinity. Though as long as, because your sample is sampled from this mixture distribution, and from the uniform, you are very likely to have values sample close to 1. And if you have such a sample there, like a value xi here, then you would rather give this value a very high density, and it's easy to do so by just shifting this triangle towards that value. So therefore, you can have a super large density for your sample, or likelihood based on your sample. And that is the problem. Yeah. And you see, why is this construction violating this MLE consistency? Because your MLE will be close to 1 as long as you have a sample with value close to 1, no matter where theta is. The reason is just because this density value depends on theta. So it's actually not a bounded density, right? It can go up to infinity. And this is something that's very weird. Yeah. But I think this is a very interesting counterexample to about more like a thought experiment to see how this could happen. Did you get the intuition there? So we're trying to find the value theta to make the joint density of our sample maximized. That's what we call the likelihood. And as long as in our sample, there's one value close to 1, we can easily set theta to that value to make that value's density super high. Yeah. So that's why the MLE will tends to be close to 1. But the true theta can be anywhere. Yeah. So the problem is just that as theta gets close to 1, this density value will go up. That's just the problem. Yeah. Okay. So with this, yeah, that's the problem with the MLE. So because of that, for good MLE, there are 5 conditions that they need to hold. So this is something we want to say more. So when can we have a consistent MLE? Yeah, and in this case, our discussion is that theta hat n is a local maxima of the likelihood function. So we're not even talking about the global optimum, but we actually, a simpler theory, let me just try to read this whole paragraph, right? Despite this example, in standard situations, the MLE tend to be consistent. And remember, what do we mean by consistent? This is something we talked about before. The typical form of weak consistency is this. Theta hat n converges in probability to theta. And for strong consistency, we need to replace this convergence in probability by convergence almost surely. But in most cases, convergence in probability is enough. Okay. Sufficient conditions for this to be the case are given in this Wald 1949 paper. Unfortunately, they are often difficult to check and exclude many standard problems. Okay, a simpler theory with conditions that are easier to check becomes possible when consistency of the global maximum is replaced by that of a suitable sequence of local maxima. This modification of the problem is due to Kramer, who gave the following conditions for the existence of a consistent sequence theta hat n, right? The sequence depends on sample size, basically, of local maximum likelihood function, satisfied, for example, by the smooth version of that counterexample we just talked about. Because that spike there is not smooth. Such a sequence turns out to be not only consistent, but also efficient. And we'll talk about that later. Efficient means the asymptotically optimal. Okay, for the existence of such a consistent estimated theta n, we make the following assumptions, 5 assumptions in total. First of all, if you have the same likelihood function, then it means that the parameter value is the same. So in other words, 2 parameter values, if you have theta 1, theta 2, that give you the same likelihood function value, then theta 1 must be equal to theta 2. And this is called identifiability. Otherwise, you will have a serious problem. That means by maximizing the likelihood, it doesn't mean that you get a unique value, right? It could be two values that give you the same likelihood function value. Then you cannot tell which one is the better estimator. Second, the parameter space is an open interval. So you don't have this boundary issue, in other words. Yeah. So this is easier to make the limits work. Yeah. Open interval parameter space. Third, and we're talking about one-dimensional parameter for now. The observations x1 to xn are IID, either with probability density f theta x, which will be assumed to be continuous in x, or discrete with probabilities. So IID is the key thing for your sample. So open is the key thing for the second assumption. And the fourth assumption is that you want the non-zero support of your distribution, the support of your distribution to be independent of your parameter value. And this is something we didn't actually have for that spike thing in that mixture distribution, right? For that one, you know, your theta changes the support, right? Where you have non-zero density values, but just for that part, not for the uniform part. Yeah. A. Okay, finally, for all the such values in your A, f theta x or p theta, this is for the continuous case, this is for discrete case, is differentiable with respect to theta. Its derivative will be denoted by this f theta prime x or p theta prime x. Yeah, this just to clarify the differentiation is with respect to theta, not for x. Okay. Okay, so these are the 5 conditions we need, and let's look at the intuition. C1 identifiability. When C1 holds, the parameter theta is said to be identifiable. To illustrate non-identifiability, this is one counterexample where it's not identifiable. Suppose that y1 to yn are IID normal with parameter of interest as eta, and we don't observe yi, we observe its absolute value, xi. So in this case, xi's distribution only depends on the absolute value of eta, not the original value of eta, because you can imagine that by changing eta to negative eta, all the signs of my y1 to yn can be reversed, but xi remains the same, right? So therefore, for both eta and negative eta, if only x are observed, then parameter eta is unidentifiable because eta and negative eta will give you the same parameter or give you the same likelihood value. This is the same thing as that MLE challenge with the incomplete data, right? When we don't observe the actual Poisson sample, but just zero or non-zero, we have some challenges with estimating lambda, Poisson lambda. Same thing here. If you're trying to estimate Gaussian mean, but your sample is absolute value, then you have problem here. Yeah, so incomplete data is always a problem. Okay, and in this situation, eta clearly cannot be estimated consistently since the x provides no information as to whether it is positive or negative. Yeah. Assumption C4. Yeah, so that one. So basically the domain doesn't depend on the parameter value, doesn't hold for the parameter triangular distributions. Yeah. And for the continuous, okay, we show in the following state results for the continuous case. They remain valid in the discrete case if all integrals are replaced by the sum. So essentially, all the following discussions are based by assuming the sample are from a continuous distribution, just for simplicity. Now the key theorem. Let x1 to xn be IID with PDF satisfying that 5 conditions. So just to reiterate, identifiability, open interval parameter space, IID sample, and the domain does not depend on theta, with the non-zero part of your density does not depend on theta. And then also the density is differentiable with respect to theta. Okay, for such a sequence with probability satisfying the 5 conditions, then there exists a sequence theta hat n, which is a function of your sample x1 to xn of local maxima of the likelihood function ln theta. We'll also write n here because the likelihood involves our sample, right? Which is consistent. That is what I said. So in this case, you can have the MLE being a consistent estimator for theta for all theta in your open interval parameter space. The local maxima are determined by setting the derivative of the likelihood equal to 0. And here, because we're assuming IID, then the likelihood is just a product. It's the product of the each data point density function, right? F theta at the value of theta, F theta x1 multiplies to F theta xm. It is equivalent, and since the likelihood is a product, often more convenient to find instead the local maximum of log likelihood. Because in the log likelihood, we can change the product to a sum of the log density, right? And then this is called likelihood equation. That is, we take the derivative of the log likelihood with respect to theta. And because of this log function involved, essentially this is all we have. And we set it to 0. And I think some of you were in my previous class. And for this one, we can actually call this derivative as the score, right? Score function. This is how we call it. The derivative of the log likelihood function with respect to the parameter. Yeah. So here, as in ln theta, the notation suppresses the fact that ln theta and ln prime theta depend also on our sample, x1 to xm. Okay. But please note that theorem does not guarantee the existence of a local maximum for all sample or for given n, even for any sample point. It only states that with probability tending to 1 as n go to infinity, the likelihood has a local maximum such that the local maximum tends to the true value of theta in probability. So in other words, it is an asymptotic result. Okay, it says what happens when your sample size is large enough. It's not a finite sample result. But when there are several local maxima, there could be a problem. Which one to choose? Yeah. So that's a problem. If your likelihood function doesn't have a global maximum. Yeah, it's not like a convex function. It's not like a concave function. So this corollary is about under the assumptions of the theorem, if the likelihood equation has a unique root, that is, if you said that it's called likelihood equation, but also a score function. If you have the log likelihoods derivative set to 0, if that equation has a unique root, then that unique root is a consistent estimator of theta, and it is tending to be MLE. Yeah. So and this result saying that even though it's just a local maximum, because we're just setting the first derivative to 0, it's that only guarantees it's a local maximum. But this local maximum can tend to, it is the MLE as the n go to infinity. So maybe we can take a look at the second part of the proof. If the likelihood equation has a unique root, this may correspond to a local maximum, a local minimum, or an inflection point, right? Because it's only about, it's just a root to this equation. So it could be local maximum, local minimum, or inflection point. In the second and third case, there can exist no local maximum, and by theorem 7.1.1, the theorem just saw, the probability of these possibilities tend to 0, right? This says about the probability of having a local maximum 10 to 1. It is thus enough to show that if theta hat n is a local maximum, it is the MLE, because there's only one solution. Suppose this is not the case, so that at some point theta prime doesn't equal to theta hat n, we have that theta prime with a larger log likelihood. If that's the case, then it means the theta hat n is not the maximum, global maximum. Then L and theta must have a local minimum between theta hat n and theta, and this contrasts the uniqueness assumption. So essentially it's saying that if you have a case like this, yeah. So if you have a case, this corresponds to, I'm just making it up, theta hat n, and this means theta prime. So if you have two local maxima, then you must have somewhere as a local minimum, and then it contradicts the uniqueness of that, of this being the only solution, only route to this one, and that cannot happen. Yeah. So that's just about the MLE's consistency. So essentially, I would say the key message is this C1 to C5. And most importantly, identifiability and IID and the C4, because C4 is the case where for many regular distributions, we have that, right? The support doesn't depend on the parameter of your interest. This is very, very important. Normal distribution, of course, it satisfies that C4. So let X1 to Xn be IID according to normal distribution with mean, chi, variance, sigma square. The log likelihood is then log likelihood, right? We write this down. And here, xi, just the ith value in our sample. So first consider the first case that sigma is known. We just estimate the mean. And chi is the parameter to be estimated. Then we take the differentiation of this log likelihood with respect to psi. We see that the likelihood equation is just setting this to 0, which has the unique solution, psi hat being x bar, right? Average. Since the log likelihood here is maximized by minimizing, right? You can see maximizing it is equal to minimizing this. It follows that this psi as the root of this first derivative is also the MLE. We verified it's the maximum, not the minimum. Of course, that x bar sample mean is a consistent estimate of psi already seen before, right? Sample means consistent for population mean. Second case, suppose next that psi is known and we wish to estimate sigma square, normal variance. The likelihood equation then becomes this. Oops, sorry. Then becomes this, and setting this to 0 has the unique solution, which is what we have here. And yeah, so 1 over n, the variance formula. Okay, in this situation, let me see. Since the log likelihood tends to negative infinity, look at this. Log likelihood is this one. Tends to negative infinity, both as sigma goes to 0 and sigma goes to infinity. So we can show that it has this minimum on both sides. It follows that theta hat is both a local maximum and the MLE. So we verify MLE. An exception is that your sample are just a constant equal to the mean, in which the likelihood is strictly decreasing function of sigma, but in this event has probability 0. So this means that this event is unlikely to happen when your sample size is large. You have exactly identical sample from a Gaussian distribution. Third possibility, suppose that you have the ratio known, mean over variance known, say that you specify cosine equals to A times sigma with A known, and that we wish to estimate sigma. Because in this case, the two parameters are tied. If you know sigma, then you know cosine. So you just need to estimate one parameter. Then the likelihood equation becomes, you take the derivative and you basically just do the parameter notation change, reparameterization, gamma as 1 over sigma. So this is the equation. And you can show that this equation has two solutions. So D is just a notation as well. So this is a two solution. And only one of these is positive. So in the range of possible values of sigma, sigma must be positive. We can pick only one of them. Then the likelihood equation has the unique solution. We're trying to verify the unique solution to the likelihood equation. Since the log likelihood tends to negative infinity as sigma variance goes to 0 or positive infinity, it again follows that this sigma hat is a local maximum and the MLE. So essentially, for these cases, we're just trying to show that, okay, for MLE, essentially in the strict way, you need to first show it is a local maximum and then try to justify that it is the unique solution. That's it. Let us now return to the general situation considered in that theorem for the consistency of MLE. Consistency is rather weak property. However, the assumptions C1 to C5, together with some additional smoothest assumptions on the density, permits a much stronger conclusion that any consistent sequence theta hat n of roots of the likelihood equation satisfies asymptotic normality. So this allows us to actually use MLE to construct confidence intervals for our parameter theta. And the only thing we need is our Fisher information. So yeah, that's what we will talk about next time. So I will stop here and I'll see you on Wednesday. Yeah. Thank you.